Assalamualaikum and hi everyone. My name is Nur Hazimah Habib Hafiz. I will explain to all of you the solution of question 1A and question 1E. For question 1A, as you guys can see, we are given the temperature distribution function. Tx equals to 3 exponent to the power of 2x, where x ranges from 0 to 1. Since the question asks for a half-range Fourier cosine series, we use the formula Tx equals to a naught over 2 plus the sum from n equals 1 to infinity of a sub n multiplied by cosine of n pi x, because the interval length L is equal to 1. First, we calculate a naught by integrating Ts over the interval from 0 to 1. This gives a naught equals to 3 multiplied by exponent to the power of 2 minus 1. So next, we determine an using the cosine coefficient formula, applying the standard interval for exponent ax cos bx and evaluating the limits from 0 to 1. So we obtain the value of an is 12 multiplied by exponent to the power of 2 multiply negative 1 to the power of n, negative 1 over 4 plus n square pi square. Substituting both coefficients into the Fourier cosine series gives the final expansion of the temperature function. So this is the final answer.
So by here, I will proceed by the question 1b. 1b, by using the first three non-zero terms of the series construct in 1a, approximate the temperature distribution. So the first three non-zero terms that we need to know is the constant term itself, n1 and n2. So picking up the half-range cosine series from the question 1a, we need to insert the first three non-zero term correspond to the constant term, which is after we insert all the three non-zero terms itself, which is the n1 and n2, we will get this final answer. So here is the graph for question 1b. The blue graph represents the original temperature distribution, while the green graph is the Fourier cosine series approximation using the first three non-zero terms. We can observe that the approximation closely follows the original function. For the next question 1c, explain why the cosine series is suitable for the insulated boundary condition in the heat transfer problem. In heat transfer, the Fourier's law states that heat flux is proportional to the temperature gradient, which is equal to this equation. For insulated rod means there will be no heat transfer through the boundary, which mathematically requires the derivative to 0. So when you take the derivative of the Fourier cosine series, every cos term will become a sine term, which is equals to this equation that I'm making here. After we differentiate and the original Fourier cosine series, we will get to this equation, which is the cos term will be equal to the sine term. So at the x equals to 0, the sine will also equal to 0. Hence, the derivative automatically equal to 0 at both boundaries. Therefore, the cosine series satisfies insulated boundary condition naturally.
My name is Siti Fadila. I will discuss question 1D. Construct the half-range Fourier sine series expansions of the temperature functions. The function is Tx equals to 3 exponents 2x 0 less than n equals to x less than n equals to 1. And the general formula for half-range Fourier sine series is Tx is equals to summations of n equals to 1 infinity bn sine n pi over lx. As we know, if we construct the half-range Fourier sine series, automatically a naught is equals to 0, an is equals to 0, and L1 is equals to 1. First, we found out what is Bn. Bn is equals to 2 over L integrate 0L Tx sine n pi x over L dx, and then substitute the number and the equations in formula Bn. We got this, and then we simplify it, and then we integrate exponents to x sine n pi x here. We use this formula to integrate this one, and we got this, and then we substitute 1 and 0 into this. So we substitute 1, and then we substitute 0. As we know, cos n pi 1 is equals to negative 1n, and sin n pi 0 equals to 1. It is equals to, and sin n pi 0 is equals to 0. So here is equals to 0, is equals to negative 1, n is equal to 0, is equals to 1. And then we got this, and then we simplify it, we expand and we factorize, and then we got the Bn. And we substitute the Bn into the general Fourier sine series, and we got this, and then we simplify it and we got this one.
Now we move to question 1e. The Fourier sine series is more suitable when the system has Dirichlet boundary conditions, meaning the function value is 0 at the boundaries. This is because sine functions naturally satisfy sine 0 equals to 0. So I'm listing out examples in mechanical systems, include beams with 0 displacement at support, heat transfer problem where the boundary temperature is maintained at 0, and vibrating string fixed at both ends. So that's all from me.
As question 2a, formulate conditions, identify the boundary conditions and the initial conditions. So for the boundary conditions, we know string is fixed at both end A and B. So we know that the U0T is equals to 0. And then here at 30 cm, so we know that the boundary condition is U30T equals to 0. So we got two boundary conditions and T is greater than equals to 0. For the initial condition, Ux0 is equals to Fx because we have two linear lines. The linear equation, we should get the equation for this line and this line. So for the first line at 0, 0, 0, 10, at 0, 0, 10, 3, the equations is y minus y naught and the grade and then y minus y naught, and then we substitute the coordinate into this formula and we get 3 over 10x. For the second line, 10, 3 to 30, 0, and we find the equations y minus 0 and we substitute the coordinate here. We got 3 over 20 times 30 minus x. So the fx we got is 3 over 10x in this range, and we got over 20, 30 minus x in this range.
So I will present for question 2, part B. So as we can see, this is the wave equation. So from this, we will be using the method of solution variable, which is this uxt equal to xx dt. So from that equation, then we will using this, which is x t double prime per xt equal to 9x double prime t over xt. So we will cut the same variable, which is xx and tt. So from that, we will get two equation, which is t double prime minus 9pt equal to 0 and x double prime minus px equal to 0. So from boundary condition, we will, by using the uxt equal to xx dt equal to 0, then we will get u0t equal to u30t equal to 0. So from these things, we will into this equation, and we will get x0 equal to 0 and x30 equal to 0. So from this, we will find the different value of p, which is case 1, which is p equal to 0. We will substitute into equation 2, so which is x double prime minus px equal to 0. Then x double prime minus 0x equal to 0. X double prime we get 0. So we integrate x become a, and we integrate again become ax plus b. So from this equation, we substitute this into this equation, which is get b equal to 0, and also we substitute using x30 minus 0. So we will get the answer. The final answer is a equal to 0. So from xx equal ax plus b, we found that xx equal to 0. So this implies uxt equal to xx dt, which is the initial equation from this method, which is equal to 0. So that we will omit this we will omit the solution. So from case 2, which is p is larger than 0, but we will let p become with lambda. So lambda with lambda squared. So from that, we will substitute into this solution, which is x double prime minus px equal to 0. So m squared minus lambda squared equal to 0. We will get m equal to plus minus lambda. So we will get into this equation, which is xx equal to a exponent lambda x plus b exponent negative lambda x, which is, so from this equation, we will get these two boundary condition into this equation. So that xx equal to 0, 0 equal to ax 0 lambda plus b exponent negative 0 lambda. So that we get the final answer is 0, a plus b, or we might get a equal to negative b. Then we will substitute with other boundary condition, which is x30 equal to 0. So we substitute the x, which is 30, into this x, and we will get the final answer is b equal to 0. So after that, we will turn this b into 0, and a will get 0. So from xx equal to a exponent lambda x plus b exponent negative lambda x, we found that xx equal to 0. So this implies uxt equal to xx dt equal to 0. So that we will also omit the solution. So that's all. Then I will pass to Livia.
Lisa, now I'm going to continue with case 3, which is p is less than 0, and we let p equals to negative pi lambda squared into these two equations. So first we're going to substitute negative lambda squared into this first equation, and then we will obtain this. And right now we're going to substitute boundary condition into the previous equation, and we will get a equals to 0 and this. So we're going to substitute it into this, and we will get this. And right now we're going to substitute negative lambda squared into the time equation, and we will obtain this. So since lambda n equals to n pi over 30, we're going to substitute it into the previous equation, and then we will get this. So we're going to put it in this equation, which is this and this, and they're going to be like this. So let En equals to Bn, Cn and Fn equals to Bn, Dn, we will obtain this equation. So by applying superposition principle, we will get this for the general solution. So by applying initial condition into this, we will get this. So we are now going to apply Fourier sine series, and this is half range Fourier sine series. So just solve it as usual, but I'm going to solve this using tabular method, which is this is tabular method 1 and this is tabular method for number 2. So lastly, we're going to get En, which is 27 over n pi squared sine n pi over 3. So right now we're going to differentiate ut and we'll get this. And now we're going to apply initial velocity into this previous equation to obtain what is Fn. So we obtain Fn equal to 0. Finally, we're going to substitute En and Fn into the equation number 6 for the general solution, and we will get the final answer, which is this. Thank you. And this is the full solution of question 2b.
For the next question, question 2c, estimate the displacement of the string at x equals to 15 centimeter at the midpoint at time t equals to 5 seconds. Note use the 3 non-zero terms of the Fourier series for the estimation. So by here, we're picking up the Fourier series from the latest question. So the first step is we finding the first 3 non-zero terms. From this equation, we trying to find the 3 non-zero terms. By this equation, I'm inserting the n1, n2, and n3 until n4. For the n3, we found that the equation is equal to 0, so it's not required to our terms, which is the first 3 non-zero terms. So proceeding to n1, n2, and n4, we find evaluating the each component and inserting the each term, we found that the each n1, n2, and n4 is equals to 0. Since the spatial or temporal wave properties at this specific time and position perfectly aligned with the nodes of the standing wave harmonics, hence the u, which is the x equals to 15 and the t is equals to 5, is equals to 0 centimeter. That's all. So here is the graph for question 2c. The Desmos allow us to visualize the vibration of the string at 5 seconds and verify the displacement at the midpoint.